Hi, everyone. We'll get started, and if people are popping in, then so be it. Today, we're going to be looking at neuromorphic sensing and also neuromorphic processing and also at reservoir computing. And both of these have applications in sort of energy-efficient machine learning. Our first speaker is Paul Kirkland, a research fellow at the University of Strathclyde in the Neuromorphic lab.
Neuromorphic sensor signal processing lab.
Yes. And he's going to be presenting his research on spiking neural networks and event-based sensing. And without further ado, the stage is yours.
Thank you very much. Yeah, so just as a brief kind of overview and overcap before I start talking, a lot of this is to try and introduce a lot of it. All I do is introduce this topic because it's somewhat known sometimes, but also it's just good to link that to artificial neural networks, which is then super synonymous, and show you the similarities and differences. So, and where it kind of fits in with that kind of scaling. So yes, what I want to cover is generally what is neuromorphic engineering, spiking neural networks, which are the main components of how you do processing within that, what kind of components and principles we have within neuromorphic engineering that makes it different, applications and advantages, and a little bit of future outlook and challenges. And then at the very, very end, I've got some just little graphics just to show you things that we've actually done research-wise, one of which is with the group here as well, so the LiDAR-based task. So high-level overview, what we're trying to look at is this idea of how do we move away from the von Neumann architecture? If that doesn't make any sense to you, that wording, then it might make sense later on when I show you a little description. But it's just this idea of having traditional CPU, GPU-based programming. But what we're trying to do is a more kind of holistic-based approach where you do lots of processing and or sensing within a neural network, which seems like a very good answer nowadays because neural networks are everywhere. But how do we do that more analogous to the brain? So not having to put things onto memory, bring them out, process them, and then put them back onto memory and doing this toing and froing. So looking at more massively parallel type systems, much sparser systems dealing with spikes and trying to be more asynchronous rather than so synchronous or clock driven. So what we really want to do with neuromorphic engineering is try and extend this kind of spectrum of processing and or sensing to this lower end of the spectrum here. So if we've got the brain in the middle, which very competent thing allowing me to stand here and talk, can use around about 20 watts. Wires, all of our computational systems, typically much higher than that, up to hundreds, up to megawatts for like large supercomputers. We would much prefer to go down to the lower end so we can have deployable systems that can be intelligent rather than having to just relay everything through the cloud with communication, because communication is not always guaranteed. So how do we get from the watts to milliwatts to like less than that in terms of processing power to actually do neural networks? So that's the kind of the main overview of what we want neuromorphic engineering to do, is bring us down to this lower end of the scale so that we can actually have deployed processing and intelligent processing at the edge. Oops, jumped too fast. So what we're trying to do here is just give you a simple comparison. So if you know what a neural network is traditionally, you know what artificial neural networks are, then you'll be kind of familiar with this idea of what a perceptron is. So you're just accumulating information from different input channels, and then with some activation function, you propagate forward information. Usually it's nonlinear, and that's what gives you the power of neural networks to combine things that are nonlinear related to each other. But if we try to look at this from the kind of broad overview perspective, artificial neural networks have existed for a long time now. The second generation, which is what the current deep learning kind of utilize, use floating point values, and you have this idea of kind of real function numbers moving between the neurons with an activation function. So you're summing and then doing an activation function. A spiking neural network, typically seen as the third generation of neural networks, changes the summation for an integration. So you're integrating now over time. So time is now implicit within your calculations. There's no need for recurrency for time. You might want recurrency for other reasons though. And then instead of an activation function, we just have a spiking function. So you're not trying to clip or manage anything. You're just trying to propagate spikes at a given time. So we're trying to replace with floating point valued numbers with precise timing information, and that's kind of where we're going to get our gains from neuromorphic engineering. This is going to be a very quick 2-minute video presentation of me trying to explain everything at once, but what we're going to see here is a couple of graphics just kind of overlaying the generics of how spiking neural networks work and how they propagate information through with these spiking kind of activations. So what this video will show, I don't want to skip over it too quickly, is spiking activations coming from the main kind of soma or neuron and passing down an axon, and then it gets split into its tree, just like any other neural network, and has all these connection paths. These connection paths are where the weights update. This is called a synapse. So typically, like any other neural network, these synapses get updated, and that's where your learning actually happens. Whether that's biologically true or not is a good question. So what we're actually doing from the soma side, from the neuron, is that we accumulate information over time. And over time, if we get above a set threshold that we have, they then cause this activation from the soma to come out. But neural networks, from a spiking perspective, are much more interconnected than our feed-forward networks that we have typically. So this is showing the kind of difference of how you can actually connect them, and it's much more complex. So to give a simple example, if we have a retina with an optic nerve and we're sending all these spatial temporal pulses down it, these spatial temporal pulses can encode lots of things like texture, motion, and color, and it's the timing and or the activations and these that are the things that are important. So as we're seeing here, this is a spatial temporal pattern that again gets kind of encoded into these signatures. These signatures are the things that then propagate information throughout the network. So as these signatures go to downstream neurons, these downstream neurons can then learn things through the activations and updating of the synapses. So if we have a bunch of these different things and they learn different correlations, some of them might be good correlations, some of them might be bad, but that can then encode and inform us of things that are going on within the scene. So it's how you take things from the spatial scene and encode them into a feature space. But we don't just have excitatory neurons as well, we have inhibitory ones that are stopping information from propagating through, because we don't just want nonsensical information to propagate through. And if we actually look at these spatial temporal patterns, this is how we do our classification. So if certain neurons fire at certain times, that can give us then quite easy indications of classifications. And this is very different from traditional computing architecture, where you would take an image and code it into its kind of a giant matrix, and then you're doing lots of these matrix and sum, so multiply and accum calculations in a traditional neural network. And this is where the von Neumann bottleneck comes in. This is literally what it is. It's passing these giant matrices from compute to memory as the thing that is actually the slowest part of the system, because you have to retain this, and you can't just retain it in the compute side. So this is what spiking neural networks is trying to do, essentially, is merge these things together. So you have compute and memory within the same thing. So if your neuron can retain information over time, it can just retain that matrix or that piece of information, and then when new information comes into it, it can compute on it without having to transfer it on and off to try and retain information. And that's where you're kind of going to get the big savings of gains. It's slightly more difficult because there's lots of architecture that has to go around to enable these things to merge compute and memory together, but that's like a kind of a very active research area just now. And something called memristors for what most people see as being the big useful solution to most of that thing going forward. So just to kind of recap on what the slide we're trying to show, spiking neural networks encode their information within timing. This is a rate encoding rather than a singular spike sparse encoding. But as you see, as the little pointer goes round, these features get encoded into either a burst and rate of information, or it could be individual spikes at the exact point in timing. So it's just kind of trying to visualize that as how we're doing our processing now. And as I said, we now accumulate information over time. So there's multiple ways you can accumulate information over time. Typically, for most of our traditional systems that are popular, we're using leaky integrating fire, which just means it's integrating over time, but there's some sort of leakage, so it can somewhat forget something. It doesn't want to retain all of information all time. But these are very simplistic ones. But then it means that when you're trying to do training or you're trying to understand some space, it's a little bit easier to start with. If you go to a high-end complex system, then it's very difficult to train. So these ones are very popular, so more likely the ones you're going to hear. But you're getting this advantage of accumulating information over time, which then makes it quite similar to a very simplistic recurrent neural network. And if you're an electrical engineer like I am, then maybe this makes more sense to you to see how the neurons are actually laid out in terms of electrical circuits, or if you like maths and big equations, then you can look at the neurons from a perspective of what simple equations they are. So for the leaky integrating fire and integrating fire ones, it's just a summation of spiking activations over time, plus what your previous membrane potential was. We do have much more complex neurons if you really want to, but trying to train a much more complex neuron just means there's so many more dynamics at play at one time. So that makes it very challenging to try and understand what's going wrong with the neurons if there's so much dynamics at play. But if you want to capture more complex dynamics from a scene, you might need more complex neurons. So a leaky integrating fire makes sense if it's a very simple dynamic you're trying to capture. But if there's more complex second order, third order dynamics in your system, then you might need more complex neurons to capture this. So along with spiking neural networks, we also have a different paradigm in terms of sensing. So with event-based sensing, we're trying to look at this, how can we marry this idea of being asynchronous, sparse type of processing with a sensing modality that is very similar in that sense. So if we try and take our eye for an example, this is what this dynamic vision sensor or event-based sensor is trying to capture. So traditional frame rate cameras capture at a set synchronized clock speed. So every 30 milliseconds or so, you would capture an image. But what if the scene is moving faster than 30 milliseconds for each frame, or the 5 milliseconds of capture time? You would then get induced motion blur. Whereas in this sense, all we're trying to look for in this case is light intensity changes and then give an exact spiking output at that exact point in time. So it's much easier to capture information if we are not sure about the dynamics of the scene. There's also one kind of overplayed or underplayed, I should say, example of this is if a dynamic vision sensor like this had no change in the scene, then nothing was happening. If it was a very boring security scene you were doing, there'd be no information to process. So then there'd be no downstream processing either. So then rather than just having a CCTV camera staring at something and nothing happens and wasting a lot of energy just processing nothing, this would actually give no information, so there would be no information processing on the back end either. So just to kind of show little examples of what these look like, so a simple MNIST example, and then one from IBM's gesture data set of just people doing random gestures, just to show what you're kind of capturing here in a kind of spatial temporal viewpoint, that there's a person in the background here, but because they're not moving an awful lot and the main part of motion is their hands are doing their gestures, that's the thing that is then most active. So then this works great in terms of if you're trying to capture motion, trying to capture activity and movement. Maybe not so good then if you're trying to do still images and identify differences between cats and dogs, but that's not why I'm here to try and sell you. I'm not trying to replace GPUs and how Meta or Google are going to do their image classifications. What I'm trying to do is have deployable systems for like robotics or other types of systems that are going to go into the world and deal with the real world. So autonomous cars struggle with these types of things because of the amount of processing you have to do in a given short period of time compared to the dynamics of a scene that's in front of me. So, picture of my face and how a dynamic vision sensor comes out, which will then magically transition to my little fun drone video. So if you want to see the real differences between it, if you look at it in slow motion, of my drone doing a sweet backflip. So in this case, you've got lots of induced motion blur within the scene. And as you can see with the event-based camera, you've actually got this smooth motion path, so much so that you can actually see the blades spinning on the propellers. So you're actually getting so much more temporal information with a reasonable amount of the same spatial information, but you're losing all the background information as well. So it depends on what you actually want in some use cases. This is going to be incredibly useful if you're trying to do tracking of objects or if you're looking around in a scene, whereas this is really nice to take pictures. The problem is that the camera industry will only make you believe that all we want is pretty pictures in life, and then that's where we went down this avenue that pretty pictures are the most important thing. But for actual terms of processing useful information from a signal point of view, the event-based sensors might just be more useful in that terms. But there's not just vision, there's lots of other sensors. no plug to all the people who helped us set this one up, of work that we did before, where you can do this, or we're starting to try and do this idea with LiDAR, so you can do it with light. If you have a single photon avalanche diode, it typically gives out a spiking output. So you can actually try and just take that information and process it live. You can actually do olfactory as well, so you can do it based on smell, so you could do chemical reactions, and then it gives out spiking activity. Same thing with touch and EMG and with audio. So audio just tries to mimic how your cochlea works by having different frequency channels and then just giving out spikes at individual times when it sees those frequencies occurring in the scene. So there's lots of different avenues to approach this from. So it kind of gives us a wide kind of gamut to push going forward. But fortunately, future outlook looks good because big names, big logos have started trying to invest in different areas of it. So with IBM, they were one of the original ones from a DARPA project looking at True North, which is a big neuromorphic chip to do processing. Intel have now got 2 developments of their system called Loihi, which is their neuromorphic chip for processing. Qualcomm have partnered partially with Sony and another company that's an event-based sensor company called Prophecy to try and get some of these event-based sensors into your phone to try and do clever like imaging or video processing so that you can reduce motion blur by looking at the high temporal resolution of your event-based sensor and then not having motion blur by then just rather than trying to do interpolation between frames, you genuinely know where everything is in the in-between frames, so just actually map that to it. And Samsung and Sony have both been looking at the event-based sensor side of things. So it's good companies to show that they're investing in it, so then hopefully they give a good, or bring in more of an audience, or wider audience. That is actually all of my slides, technically. But this is just like a little application ones that I'll talk through. So the top right-hand corner one is work that we're trying to do is now, where we're looking at capturing information live from a LiDAR sensor or SPAD, and then you're trying to do that processing over time to actually reconstruct a full scene. This is from a single point, so some of that's magic, that it can understand spatial resolution, but as long as it knows what the scene is, there's a lot of machine learning-based kind of data gathering and feature extraction that you can do from that you can reconstruct a scene. I should go backwards and forwards. That's the one that plays. The little fun video here is trying to do a tracking-based example. If you're trying to track a small object within noise, if you're trying to use Kalman filters or trying to use particle filters, it's very difficult to try and see with in between the noise. But if you do a very simple pass with a spiking neural network, you actually get a very simplistic output where you're actually only looking at the thing that's changing or moving very highly in the scene. And that's kind of exploiting the sparsity because of the temporal resolution. If you actually look at like 1 microsecond changes within a scene, not much happens ever, but actually there's much more signal to noise at every single one of those different instances. So if you very smartly accumulate that information over time, then you get a very useful output. And the last one is actually a more commercial idea for this, which is looking at a weld pool. So this is a TIG welder. So this is the weld pool coming off the back of it, because you need such a high dynamic range to look at a very bright arc from a welding project. You can actually see the kind of weld pool forming and bubbling around, and this indicates how well the weld is actually formed to the piece of metal underneath it. So typically you do this with HDR cameras, but then the processing side of it is quite a lot of information you're trying to process, and obviously the temporal motion of a weld bubble is quite a thing that exists in a very small amount of time. So you want to be able to extract all that information and then maybe do real-time control for that. Because if you're a human and you're welding, you can see the weld and see that it's bad and then maybe adjust ever so slightly. But the robot has to do that via sensors and through computation. So there's no point running the weld and going, oh, well, it's rubbish. I can go back over this again, especially when you're getting to high-end welds. So this is not for cheap, easy things that you can weld together. It's for more precision welding-based tasks where things only get welded once and it costs $500,000 to weld these 2 pieces together. You make sure you want to do it correct. So overall, that is all of my applications, and I'll gladly take questions. Not like to advertise at all.
Thank you for the talk, Paul. Can I start off with a question about scalability? So you kind of mentioned that you're not trying to replace the GPUs and the sort of traditional AI paradigm that exists, but how scalable do you feel spiking neural nets are, either in software or done actually in neuromorphic hardware? Where do you think that lies now and in the near future?
Okay, yeah, so for scalability is always a big question because as we've seen with deep learning, everything's scaled to massive sizes, and large language models are large language models for a reason, is that they're large. So scale does help. And some of the systems I use very simplistic training models to do things, and they don't seem to scale very well because that's very challenging. But you can get spiking neural networks. A spike is non-differentiable, that's sad. But if you just use a surrogate gradient, hey, you can use backprop. So life solves itself. And there's been very big, large-scale models using like surrogate gradient backprop with spiking neural networks. So there is a spike GPT, if anyone's really interested. So you can use that version of ChatGPT to actually do large-scale networks. But then you're losing a lot of the power saving and kind of other elements that Neuromorphic is going to want to bring with it. So low latency and power. It doesn't really fit in with that kind of narrative. So there's a kind of, I think that is that spectrum as the finding your point on it of like how much sparsity, latency, power saving do I need versus how much processing do I actually want to do. But I mean, our brain can do all of that in 20 watts, so maybe we're just naive to the approach of what we're actually.
Yeah, and I have one more. As I was looking through your slides, I was thinking, there's a lot of data sets, a lot of models that work well with traditional computer vision. I'm talking like RGB images, RGB videos. How do you think this transfers to event-based sensing? Or what experience do you have with that?
Okay. So it's a good point and good question to make. So there's people have started creating event-based data sets now, but because there are so many data sets from previous ones, it really then depends on your task. But this becomes the issue, like if you want an ImageNet task, where you're just looking at images, just use a CNN. Like, please don't bother me. If you're wanting to do like, I don't know, a gesture detection, little tiny robot dog or bee or something like that can maybe identify bee dances, good luck trying to run that on a CNN. So then maybe come and speak to me about that, and then you'll try and capture it in this event-based sensed world to try and save all your energy in doing these things. There are people who like to do the merging between two things, and there is a few things that now do conversion from one to the other, but you've lost all the temporal information that was there. So one is capturing in microseconds, another one is capturing in 30 milliseconds. So you're just doing amazing interpolation and then turning those into events. So, but you've kind of lost the essence of what you're doing. But because deep learning is so popular, it's still a very active area that people just convert, train on it. Look, I got good in MNIST, I got good in ImageNet, and you're like, but why? I don't understand. So finding the kind of tasks where it's going to be more constrained and you have a lot of issues. So space is becoming the bigger one for this. Because space, you are stupidly constrained. And you can't just pass it off to the cloud because you're above the clouds. There is no cloud. So it becomes really challenging to go, how can I do lots of onboard processing that might also be adaptable, might also be low latency? I can't, these things are required. So it's kind of a waffly answer, but yeah, there are ways you can merge it across to try and get some more data. And there has been people who have done recurrent vision transformers using event-based stuff, which might be useful in terms of just having a big repository of things that you can maybe take from or learn from what they've actually done. But I feel like you need to be a bit more focused on your tasks for what you're doing for some of these.
Maybe one more question. No, I was just wondering. I think the idea has been floated before that the reason biological neural networks encode the time domains because their latency is awful, right? They have very high latency. And you can actually, encoding information in time domains is actually kind of orthogonal to analog neuromorphic architecture. You can have synchronous analog architecture, right? Neuromorphic architecture that uses a clock but stores information continuously because the last few bits of a neuron's weights matter less than the first few bits. So, given that, for capturing real life events, I understand why you might use this. The latency is real life events take place over like 30 seconds. So the latency is not an issue. But for very fast things like, well, a lot of machine learning stuff will happen very quickly anyway. Is it actually worth it? I mean, when latency is really low.
Yeah, so in those cases, but then you can do the opposite, where you start to exploit the terms of how you can do computation on silicon. So this is where Intel and all these other companies, their chips are not analog chips, they're digital chips. So they're using traditional architectures and traditional CPUs to do some of these processing and doing time multiplexing because they had so much time on their hands. But you can still want to try and exploit some of the idea of asynchronicity and event-based processing and information, and doing this combination of like memory and compute in one node. So lots of those elements still have to come into it as being super useful, even in terms of latency, depending on how much you want or how much you don't want. So you can exploit kind of both ends of the spectrum if you want. Like, this is where we're trying to go with this. Like, our brain is a very complex mess of biology and chemistry doing these spiking activations. But if we could do that on silicon faster, what can we learn though from the connection patterns, from the types of processing that you're doing, that you don't have to just do this matrix, like multiply and accumulate type equations? What else can we actually do that we could actually save time? And the bigger one is more the asynchronicity. If you have lots of sensors connected at the same time, it's very difficult to actually try and aggregate that information together, because then you need like a common time, a common framework on things. If you have multiple sensors that don't have timing on them and can't share timing between them, how do you synchronize two sensors that are not attached to each other? It's literally just why laser light timers for like doing distance things are so complex, because this one has to tell it the exact time that one has, and how do you do that when there's latency or communication and everything? So if there's other ways you could do asynchronous-based processing, it just takes away a big headache for engineers when you're trying to combine sources of information that are at different rates together. And that's what your brain does. Things are slow, things are fast. You're thinking about what you're going to have for breakfast. You've thought about that thing you said to that person at the bus stop once and they never replied to. All these things are slowly being processed in your brain at the same time, and it just takes what it needs at a time. So,
Thank you. Okay, we'll have one more question, and then
I'll answer super quickly.
we're on time. Okay,
Yeah, or I'll just catch you afterwards.
Okay, great. Then let's thank Paul again for that amazing talk. And our next speaker is Julia, who is Julia Marcucci, is a research associate in the Extreme Light Group.
Very long press on the buttons.
Okay.
And she's looking into reservoir computing and basically everything to do with making AI more energy efficient. So without any further ado.
At least I try. Yeah, so thank you very much for being here. This is the title of my talk, Towards Sustainable AI Hardware, or to be rephrased, Advancing Wave-Based Reservoir Computing for Eco-Friendly AI. I will tell you in a moment. I hope that at the end of this talk will be clear what wave-based reservoir computing is. So, as you said, I have to push very... See? Okay. So a little bit about my research. I spent the last, 5 years of my life everywhere in the world. And this is kind of related to the work I've done. And again, the work I've done revolves around analog computing for AI system with a focus on harnessing the complexity of nonlinear quantum random waves. So let me tell you more about this, if I may. Okay, no, I went too fast. I pushed too much. So about nonlinear and random waves, the first part of my work is about optics, and it happened in Sapienza University of Rome, and these are the two papers that came out from it. And then after, I moved to the University of Ottawa, but didn't work actually on neuromorphic computing there. And I instead continued my work on neuromorphic computing in a neuromorphic startup in London, where I actually focus on the design and the optimization of a hydrodynamic system. And then right now I'm here working on many different things that I hope I will have time to talk with you in a moment. But the last two topics we actually explore were about the development of neuromorphics in visual brain-computer interfaces, and also the idea to move to the quantum realm, developing quantum reservoir computing. So my talk, the outline of my talk is actually very simple. I will tell you why I'm doing this, what I've been doing, and how I plan to continue to explore this field. So why I'm doing this? To make the world smarter and greener, or at least I hope so. So in December 2015, the United Nations met in Paris, and they established that we need to decrease our emission by 45% by 2030 and achieve net zero by 2050 to limit the global warming to no more than 1.5 Celsius degrees, because if we go farther than 1.5 Celsius degrees, what happens is that the effects can be catastrophic on our planet. And why is AI related to this? Well, in general, computing systems are related to this, as we can see from this report conducted by the Semiconductor Research Corporation. So if we are not able to create new paradigms for compute by 2050, we will reach the world's energy production as energy consumption. So this means that there is a real reason to develop this field. And I think that this dramatic scenario tells very well why I moved to work on this. Then, why is this analog reservoir computing development something that is related to making the world smarter and greener? Well, first of all, it's because it is based on artificial neural network paradigm, which is the reservoir computing, that can merge together the best of both worlds, analog and digital computing. So it is indeed based on, it is not based on states, but it deals directly with continuous data, which is a feature of analog computing. But on the other hand, it can be not only fast, but ultra fast, can have a high accuracy, ultra low power consumption, and I will tell you in detail why is this. And it can be easy to use, but also very interesting from a scientific point of view, because it is based on complex dynamical systems. So it actually offers an holistic approach where the complexity can solve complex problems by itself. And this is the artificial neural network architecture. So, or at least a sketch of it we can find in reservoir computing scenarios. So now I'm just talking about software, and I will tell you in a moment how to move this architecture to hardware. So reservoir computing is based on the exploitation of nonlinear and stochastic transformations in a fixed high-dimensional dynamics. So we actually have an input layer that is mapped into this reservoir, which offers this fixed high-dimensional representation of the input data. And then everything is mapped again in an output where in the output layer is the only part where the training occurs. So all the training happens just in the output layer. And let's say having a very, very rough overview of the artificial neural network zoology, which is, of course, not complete at all, and it cannot even be updated because the development of these artificial neural network architectures have a pace that cannot be followed. So let's say that we consider all the possible architecture in the artificial neural network world, where here we have neuromorphic computing, here we have recurrent neural network, and in theory it's not plot there, but here we should have the convolutional neural networks. So what we can see is that in the neuromorphic computing world, there are the spiking neural networks that were explained so well before by the other speaker. So I won't talk about that, but I work in this realm here in the reservoir computing. So at the intersection between spiking neural network and reservoir computing sets, there is the liquid state machine, which has the property of being a universal approximator. While instead at the intersection between reservoir computing and recurrent neural network, they are the ego-state networks, which are the most important architectures to realize analog reservoir computing. So the ego-state networks inherit from the recurrent neural network the Turing completeness. However, they are not universal approximator. There are versions of them but not in general. And there is a degenerate version of these ego-state networks, which is actually not recurrent but fully feed-forward, which is the extreme learning machine, which was proven to be a universal interpolator, even if with several limitations. So in this realm, again, here there is another plot of this artificial neural network architecture, where again we have our input layer, reservoir, and output layer. We can see the math of it. So, and we can think of dynamical systems while we look at the math of it. So the encoding layer is actually the definition of a multidimensional array of initial conditions for a dynamical system, while instead, the reservoir is a complex dynamical evolution of the input layer, which is transformed using an encoding map, and some through a transformation of the recurrent term, so our output at the previous time. And the decoding is done just using linear regression, while the training occurs, as I said before, just in the output, finding the best solution for this interpolating matrix W out. So if we want to produce such an architecture in the hardware world, what we need is to have these 5 features in our hardware system. So we need to have high dimensionality, so we can distribute and separate the input data, as I explained before. We need complexity, because otherwise the processing doesn't have any good performance. We need fading memory, because if we don't have fading memory, we cannot have this term here that is still acting in the reservoir. And tuning correctly the complexity can give us input-output distinguishability or separability, and input-output reliability. So I put inside 2 inputs. These are distinguishable in the output, but they don't diverge. So my point is, why don't we exploit the complex evolution of waves in complex systems? And that's the reason why I talk about wave-based reservoir computing. So now I'm just going to tell you a lot of stuff I've done in this realm. So starting from exploring nonlinear optics, I will try to be very fast here, because there are a lot of details, and it's not related to the scope of this talk. But the main idea is that we can always map our hardware, which is a real hardware, in architecture of artificial neural network. And in this case, this has been done using as encoding free space propagation of plane waves that are generated using spatial light modulation. And instead, the reservoir is ruled by this equation here, which is the nonlinear Schrödinger equation, which means that it's given by the propagation into this crystal here, which is a crystal where the light is self-focusing, which means that the velocity of the light goes towards the peak of the intensity. So the higher the intensity, the higher the velocity, and the more the light during the propagation. So in a system like this, the decoding is done using a CCD camera, which is just imaging the light that comes out from our system and defining the output channels. And the training is performed by computing this coefficient here that just provide the linear regression I showed you before. So this system here doesn't have any recurrent term. Indeed, is in the structure of the extreme learning machine, which is the feed-forward, degenerate version of the ego state network I showed you before. Couple of tasks we try to perform to benchmark the system. So we can see that there are two different conditions to make the system work. The first condition is related to the geometry of the system. And it shows you that if I have as a number of output channels, a number that is much lower than the number of training channels, 20 and 200 here, and here I'm doing the interpolation of a sin x over x function, where the theoretical points are the red circles and the computed points by the optical machine are the blue dots. So when the geometry is so unbalanced, as you can see, the interpolation is not very well done. While instead, when the geometry is tailored, so for example, here the number of training points is equal to the number of training channels, we can see that we can move to the exact learning regime. So we have in this plot a learning transition due to the geometry. And instead, if we fix the number of output channels, but we vary the nonlinearity, that in this case is given by this coefficient chi here, that rules the nonlinear, expresses the nonlinearity of our reservoir, what we can see is that we can have the same learning transition. So in short, we have two fundamental conditions. One is about the geometry and the other about the nonlinearity, which is the only term that provides complexity in this system. And so complexity is needed to solve complex problems. We did the same doing classification. Now the encoding strategy changed. I didn't tell you before. Before it's been done in phase. Now it's done in amplitude. For people who knows the wave propagation complex system, is clear what I mean, but it's not a point. There is always a strategy to encode information in the system. And here we use two different strategies. So with this encoding strategy, we can classify the age of the abalons, having a multivariate series in input, which just one scalar in output per item, and the array in input are array points. And you can see more or less the same. So still two learning transitions, but what is interesting is that if we vary the encoding strategy, we are also changing significantly the amount of complexity, so nonlinearity that is needed in our system to move to the learning transition, because now it's 400 and before was 20 in arbitrary units, but still you can see that there is an order of magnitude more. So then we moved to the lab. We said, let's try to do this. But actually, the experimental world is always more complex, so we couldn't exploit nonlinearity because we got to chaos for these very simple tasks. So the idea is to move to more complex tasks, but for this very simple task, we use instead a random mask that was superimposed to the encoding layer. So it is like if our device, so the SLM for people working in optics, is providing here both the encoding layer and the reservoir. And we did similar things, so classification, interpolation, and stuff like that. Then, in the startup, we work on these hydrodynamic designs. And the concept here, again, is very similar, still the fully feed-forward degenerate case of the generate version of the ego state networks. Now, of course, the reservoir change. So the model equation is the KBK equation, which is an equation that expresses many different complexities in hydrodynamics. So there is the surfer wave breaking, then there is a term for the dissipation, a term for the dispersion, which is very similar to the nonlinearity we can find in optics, and a term for weak turbulence. And in the ansatz in which dissipation and turbulence are small enough, we can have our encoding in linear solution of just the KdV equation, which is the equation with these two terms and this term. And when they collide with a soliton, so a traveling wave which conserves its shape during the propagation, we can see that the dynamic there is complex enough to realize reservoir computing. So let me go fast here, maybe. Okay. I'm not going into details of these last two works. Again, the first one about the visual brain-computer interface, but I can tell you that the encoding is done using frequency multiplexing. The reservoir are steady-state visual evoked potentials, and instead the decoding is done using EEG. So as you can see, as long as we have a complex systems, we can actually do something in the computation domain. And in quantum optics instead, and if you are really interested, you can also find of this paper, the archive version, we use as input Fock states or hybrid version of Fock states. The reservoir is given by boson sampling and the detection by photon numbers or by a photon number resolving detector. So how I want to do this stuff? Understand that there is a sweet spot to make it work, but I don't find it's a sort of a complex problem, also this one. Okay, so I pushed twice, but it's okay. How do we want to do this stuff? Now it's important to understand, because as the first inventor of the ego-state network, Herbert Jaeger, showed in his last work published on Nature Communication, we can actually make computing machine out of whatever physics offer. And if I can be honest, I feel a little, let's say, criticized by that, but in a very good way, because as you can see, I mean, it's a me. I'm kind of showing that we can actually make computing machines made out of whatever physics offer. So my point is, how can we make it better? Optimizing them, and the optimization problem has been shown. It's a complex high-dimensional optimization problem, because the idea of optimizing the compute efficiency, it's not related to the optimization of the energy efficiency, which is not related to the optimization of the carbon emissions. And also because, as Lord Kelvin wrote, when you cannot measure when you cannot express it in numbers, your knowledge is of a meager, unsatisfactory kind. So we don't want to have a knowledge of an unsatisfactory kind. So the idea is to move through optimization. Am I running out of time? 5? Oh, okay. So we did this. So the first step towards this direction was in the neuromorphic startup to optimize the hydrodynamic reservoir, and it happened in this collaboration with the Oslo Met University, where we use an evolutionary algorithm with a fitness function equal to the absolute value of the readout matrix determinant. So the W out that I showed you before, you compute the determinant and then the absolute value. Why so? Because we showed that if this is greater than 0, we are in the interpreting regime, so we are actually doing exact learning. But then if we maximize the absolute value of the determinant, we are actually improving separability. So I will go very fast here. The main idea is to use, your first individual, then you mutate this through Gaussian notation, you get a new individual, you evaluate your fitness function with phenotypic descriptors that are the mean value and the standard deviation of measured amplitude and frequency. That's why we evaluate on a real reservoir. When I say real, I mean it's still a theoretical experiment. We're still talking about software in this case. And then everything goes into a map elite algorithm, which extracts the best individual again, and we go into this loop until we don't find the right solution that gives us the small error we are looking for. So two interesting results here. First of all, related to our next NOR gate, which was the task that was accomplished in the previous paper, the one that I showed you before, with based on the KBK equation, and it's that we can get 100 times the performance of the hand-tuned implementation in the paper if we actually use as a phenotypic descriptor the amplitude in this case, and not the frequency, because the amplitude is what is actually ruling the nonlinearity in KDV equation. And if we think instead to interpolation task, which is a task where we can test our generalization performance, we can see that the higher the separability, the higher the generalization, because through our optimization, we can move to an error that is of the order of 10 to the minus 1. So we are decreasing the error a lot, just improving the separability of the data, which is something that it's kind of a novelty in the field. Then, of course, the generalization here is still not performing very well, because the sigmoid interpolation here is on a unitary, normalized, sigmoid, so 10 to the minus 1, it is still the hell of a error, but at least it's showing a certain trend. So next step will be to try to control the reservoir, actually. So using nonlinear control in a system that is based on multimode fibers. I'm working with Juan Sebastian Todero Góngora in the University of Loughborough. But let me stop here and thank you for your attention.
Let's start off with Sam.
Of course.
Unless you want to start
We can talk later.
I just had a quick question. So you talked a bit about optimization through the separability of the response matrix?
Yes. Yeah. Not the response was. Yeah, the response actually. Yeah, we can call it this way.
Okay. I think, and that was, and you did that by maximizing the determinant of your response matrix.
Yes.
Okay. So I have an idea about that, but I was wondering how do you give me an interpretation of separability? I don't quite understand what that means.
Essentially, the main idea, is that when you consider reservoir computing and you consider your reservoir, that for you is just processing things in a blind way, so you don't have access to it. You can consider it as a black box, But we can think of it instead as the projection of many, many hidden layers in a deep neural network architecture. But this projection must be done in a way that is actually sparse. Okay, so to make this projection sparse enough, we need to separate our input data. Okay, so the separation we have inside the reservoir is then, of course, also detected by the output layer. So when I consider the response matrix, which is actually the matrix that I can get from the output layer, okay, this is just an imaging, if you want, or a detection in whatever fashion of the separation that you have inside. So algebraically, considering the determinant of your response matrix, it means that you are considering the characteristics of the vector space that you're actually generating through your reservoir.
So is it sorry, I don't mean to dominate.
No.
Okay, so is it a sort of, you're measuring the orthogonality of your projections in feature space, separability?
Yes.
Because there's a nice interpretation that ties in with our social number resolving stuff, where
Yes.
you're maximizing the determinant, you're also maximizing the product of the eigenvalues, and you can show with Lagrange multipliers that if you have some object with some length, if you break that into sections, you maximize the product by making the length sections even, And what that means is that your eigenvalues, which correspond to the different orthogonal features that you're generating in your projection space, are now evenly weighted. So you have more evenly weighted orthogonal. So is that the same thing as separability?
I think yes, but I think we should move this conversation to another. But yeah, let's talk more about this.
Yeah, absolutely fascinating. So
Thanks.
the use of your equation on selection at this fourth order.
Yes, yes, of course. So you are talking of the KBK, I guess.
It's around the famous equation you have.
Yeah.
Yes, so
Yeah.
this is the Kuromoto-Sezhinsky
Yes.
without dispersion. So the universality of that is studied extensively in
Yeah, of
physics.
course.
So the choice of parameters, alpha, beta, gamma, they have significant impact.
Yes, of
So
course.
This is an equation which goes from ordering dynamics all the way to turbulence. So what I'm wondering, this is my first time reading this concept of reservoir.
Yes. Amazing.
So are you selecting the parameters alpha, beta, gamma on the fly as you go? Is that part of the reservoir process where those are degrees of freedom, or are you selecting those and then pumping your data?
Okay, so we work here in an approximation which we actually are considering mostly the KDV equation. We're starting from this equation because it represents the...
But do you fix the parameters for the whole computation, or do you adjust them as you go?
I fix the parameters, yes. I fix them. It's yeah.
Maybe last point to come back to this here. So I'm intrigued by the reference of orthogonality, because in some sense, from a PDE standpoint, when you have partial equations of the structure, there's inherent geometry in those equations. There's concept of orthogonality there, which are not Euclidean. Your point actually kind of brings up an interesting question for me. What type of inner product do you have in mind? There are inner products associated with these equations which are not Euclidean. So that could also be another thing to do.
Yeah, so to try to give a little of food for thought, the problem of exploring the optimization of the systems relies on this. So this system, they work at the edge between stability and chaos. And this has been, how long do I have to answer?
We should be wrapping up, but we can talk afterwards. They're going to kick us out of the room shortly, but we've got time.
Okay.
The last question.
So for now, everything is untuned. That's the point. All the computation is untuned, and you just use a sort of experimental way of doing things. So like you find one configuration, it works, you stick with that, and you try to get the best out of it. And that's the reason why we're trying to optimize, but there is a lot to discuss about what you just said and what Sam said before, definitely.
All right, let's thank Julia again.